Hello, this will be a demonstration of Proposition 8 from Book 6 of Euclid's Elements, which says that if in a right-angled triangle, a perpendicular straight line be drawn from the vertex or from the right angle to the base, the triangles so made will be similar both to each other and to the whole. What that's going to look like is we're going to have the triangle ABC. That A, B, C. And from the vertex A, we're going to have the straight line AD drawn to the base BC, like that. And what we're going to prove is that the two triangles so made, that is, the triangles ABD and the triangle ADC, that these two triangles are both similar to each other. That is, that the triangle ABD is similar to the triangle ADC, and that both are similar to the whole triangle. That is to say that the triangle ABD is similar to the triangle ABC, and also that the triangle ADC is similar to the triangle ABC. Now, knowing that the angle BAC is equal to the angle ADB, we know this because they are both right angles. We know that the angle BAC is a right angle because that was given, and also that the angle ADB is a right angle because it's perpendicular to the base. So by postulate 4, all right angles are equal to each other, so the right angle BAC is equal to the right angle ADB. And the angle ABD being common to both the triangles ABC and ABD, then we can say that the third angle ACB is equal to the third angle BAD. That's by proposition 132 and others. Again, I've explained this, that if two triangles have two angles equal to two angles, then the third angle shall be equal to the third angle. Okay, so what we now have is that the triangle ABC is equiangular with the triangle ABD, which means by proposition 6.4 that the sides about these equal angles will be equal to each other. That is to say that BC is to BA, just as AB is to BD, and just as AC is to AD. So the base BC is going to be to this side AB, just as AB, which is the base of the triangle ABD, is to BD, and just as AC is to AD. These are all the corresponding sides, so they're all going to be proportional to each other. Okay. Now, these two triangles, ABC and ABD, are equiangular and have the sides about the equal angles proportional, which means that by definition 6.1, these two triangles, ABC and ABD, are similar to each other. Now, we can prove in a similar manner that the triangle ABC is similar to the triangle ADC, so that would be by proving that the triangles ABC and ADC are equiangular, which is very easy. And then by 6.4, the two triangles being equiangular, their sides are proportional. So we've just proven that the two triangles ABD and ADC are similar to the whole triangle ABC, which means that what is left for us to prove is that the two triangles ABD and ADC themselves are similar to each other. So knowing that the angle BDA is equal to the angle ADC, again because they're both right angles, and by postulate 4, all right angles are equal to each other, and the angle BAD having been shown to be equal to the angle ACD, this was shown in the first step, we have two triangles where two angles are equal to two angles, which means again by proposition 132 and others, that the third angle ABD is equal to the third angle DAC, which means that the two triangles ABD and ADC are equiangular with each other. Now, of course, being equiangular, by proposition 6.4, we know that the sides about the equal angles are also going to be proportional, which means that BD is to DA, just as AD is to DC, and just as BA is to AC. So BD is to DA, just as AD is to DC, and just as BA is to AC, which means that the two triangles ABD and ADC have been shown to be equiangular and have the sides about the equal angles proportional, which means, again, by definition 6.1, these two triangles, ABD and ADC, are similar to each other. And this is all that we set out to prove, that the two triangles ABD and ADC, which are made by the perpendicular AD, are both similar to each other and similar to the whole ABC. And having thus proven this, we are done with the proposition, therefore, etc., QED. Now, there is a porism appended to this proposition, that if in a right triangle, a perpendicular straight line be drawn from the vertex to the base, then the perpendicular straight line is the mean proportional between the segments of the base. This was shown in the last step, that as BD is to DA, so DA is to AC. Again, this proportion as BD is to DA, so DA is to DC. And this is exactly what a mean proportional is, that it's that it has equal ratio in between two other magnitudes. So between the two magnitudes BD and DC, we have the mean proportional of DA, so that as BD is to DA, so DA is to DC. And this is another case of the porism of a proposition being more important than the proposition itself. So this is, again, one that you're going to want to remember, not just for the rest of the elements, but also for any other geometry you decide to do beyond the elements. I've got nothing else to say about this proposition, so I'll end the video here and move on to 6.9.